Okay, Ganesh, really quick. I'm going to give you a quick overview of our challenge.
All right.
Then I'll show you, well, I guess I can show you quickly the map that we have, some things that we have considered, and then we'll just give you the floor for you to share whatever comes into your mind that we may be missing. So basically, really quick, here is a simulation of the solar cycle. When you look at the sun, you have all these structures that you see at the surface in the forms of sunspots. They are tied to magnetic structures in the interior of the star. So if you can really understand the properties of your spots, you can learn a lot about the stellar magnetism. Now, unfortunately for stars, not the sun, we don't have access to their surfaces. We only have access to the modulation of the amount of light that these objects produce. So here is the sun with a spot, and this light curve is showing you how the existence and the presence and the crossing of the spot darkens the surface of the star, of the sun as a star. But you can look at this and infer. You say, okay, well, there was a crossing, and this is a sunspot, and maybe it's this big, and it takes this long, so I know how long it rotates. This is the data that we're working with here. This is something like this, but for an actual star measured by Kepler. And this is telling you how much light we're receiving from that star. And you can see that it is being modulated, and the nature of that modulation changes with time. There are big dips and double dips and shallow things. And you can almost imagine that this is a big sunspot crossing the surface of the star, and this is another, for example. Or it could be this one returns and things like this.
There are other contributors to this, like fluctuations, than the spots, right? Is this the case? Okay.
Yeah, but we're going to be working with data whose main contributors are the properties of the star and the crossing of the spots. There are several things that will affect how this light curve looks. One is the rotation, so how the rotation of the star and the properties of that rotation. The other one is how many spots you have and where you have them. So if you imagine the star as a three-dimensional object, you may have spots at the same longitude and they will cross at the same time, or in different longitudes, and then you will see one first and then the other. The other one is the spot lifetime. So each spot lasts for a certain amount of time, and it will disappear. And then another one will take its place. So that's another thing. And the last one is the stellar inclination. So whether you're looking at the star from the poles or from the equator. All these things are things we would like to say something about based on this light curve. So we would like to see these light curves and say, oh, this is a curve that is produced by a stellar rotation with this range of possibilities for rotation, for coverage, for lifetime, and for inclination. And we have models. So this is a model of a star that has certain properties and certain amount of spots of certain sizes, and these are rotating. And here at the top, you're looking at the star from the pole, so you can see you don't see any change, like differential change in brightness. Here you're now a little bit inclined, more inclined, and from the equator. And you can see it's the same exact spots, same physical properties, same rotation, but they will produce different light curves. So there is a very large amount of degeneracy in this problem. And we're trying to go from the blue curves into being able to say something meaningful about the maps that you see here. Some stars have planetary crossings that will look like this one, where you have a planet that crosses the surface of the star, and you see it. Sometimes it may occult spots, and it will change the light curves in a different way. So this happens very quickly. So here you have these things is days on the light curve that I show you first, and you see these tiny little dots here that appear at the bottom. In this particular stars are likely crossings. And if you zoom in into one of those crossings, you can see the planet cross in a matter of hours. and as it occurs spots, you can make an inference on that. So that's basically the general idea, is that from these light curves we can learn about the stars, but it's a very degenerated problem. So how do we go back into something meaningful, given the fact that we have pretty sophisticated models of what the stellar surface will look like? So we can generate many of these light curves and try to match them with these and make an educated guess about this. And here is a general quick map of our challenge so far. As we go today from having stellar light curves, so our data, and models of these light curves that we can run at will, and we can create as many as we want with as many properties as we want. And we basically want to combine them in some meaningful way to guess, to produce and verify the relative uncertainty for stellar spot maps for all these stars. And there are two kind of branches that you see here. One has to do with all that we everything that we're doing to the data, cleaning it, understanding it, processing it, and passing it through our pipelines and so on. And our models. So we can generate many models. And ideally, we will use these models in some way to infer and interpret what these light curves mean. Mm-hmm. So that is our challenge in 5 minutes. So you are an expert on probabilistic programming, and this is one of the reasons why we chose you. And you have worked a lot on learning models and use them to make these kinds of inference. So please tell us, how would you do this? How would you solve it? And what would you do?
Okay, this thing is awesome, by the way. Like this Miro website, whatever it is. Oh my god! Okay, so I took notes here.
Ganesh.
What's that?
Sorry, before we start, to give Ganesh a couple of seconds to collect his thoughts. Tansu had to drop out because his internet died. Would it be possible to start recording so that he can catch up afterwards?
I really want.
I am recording.
I am recording.
Yeah.
I see his pointer in the Miro stuff. He's around there. I noticed that. Yeah. Okay. So one thing that struck me. Are you recording? Okay. One thing that struck me immediately is like you saw this like so I don't know how to show this, like this sun, right, in the beginning, Andres. So I mean the stuff inside the sun, like, and like the activities within the sun, and like how these are observed on the surface, right? There is a direct analogy between that and like what one would describe as like latents and observables in probabilistic modeling or machine learning. So basically you have like a perfect analogy for that thing. Like you have this sphere, inside that there are unobservable stuff. They correspond to latent variables. And you have stuff on the surface, or like stuff emanating from the surface, that correspond to observable variables. It's like a one-to-one analogy. It's like a perfect thing for probabilistic modeling. And you want to like infer stuff about latents given the observables, right? That's like the standard setting in probabilistic inference. So maybe this is kind of obvious, but I really like this as an example to the degree that I can like introduce my research to people with this analogy or something. So that's one thing. So you have this toy model on the right hand side, right? You actually said like a advanced model, but like I don't know if I should use the name toy model for this, but
yes, yeah, we have the toy model.
Yeah, I mean it looks pretty advanced compared to some other toy models I've seen in my life. So it's awesome. It's looking great. So you can do a lot of things with this sort of modeling approach. Like this is completely, how do you say, like this really is compatible with the stuff I've been doing the last years in my career with this probabilistic programming stuff. Basically, you have a model that you can calibrate to like do model-based inference on your real data. So I would definitely consider that type of stuff if the people in the team have some like background or experience or like interest in this type of thing. Like it's one of the things you can definitely attempt.
Can you repeat what is the keyword there of what we can attempt?
I mean, probabilistic programming you can do. Probabilistic, that it's definitely like some model-based inference. The most generic term for this thing would be model-based inference. So this is like, so there are two things, for example, like two rough categories in machine learning. You could do like data-driven stuff, like deep learning, like you have some large data set. You are trying to learn some relationship between the data in the data set. Like basically you are trying to learn your model from data. Like you have lots of data, you don't know how to model it. Let's say human faces, people generate like fake human faces, right? There is a generative model of human faces in the nature. It's like the biology is generating human faces. There is some process, generative process, but you don't know how to model this. You cannot sit down and write a model, like program a model that will generate human faces pixel by pixel. It's an impossible task. But if you have millions of human faces as images and you can learn a generative model, so in deep learning, when people say generative model, they most of the time refer to this thing. You learn a model from a data set. But so the other alternative is doing something model-based. Model-based inference refers to the other alternative, where you start with a model, you have an understanding of the phenomenon you are studying, you can model it, you can like express the physical relationships, how things depend on each other. You have like basically this applies to science a lot, like you in scientific fields or physical sciences, you can model stuff like you did here. We see like examples of your model running on the right hand side. So there are techniques to work with this model and like condition the out, like how can I say, like I'm trying to calibrate the language, but so because I don't know about people's backgrounds, but like there are techniques already, like lots of techniques that will allow you to work with this model here, maybe make it a bit more complicated, maybe calibrate it to real data or something, but like you can get your predictions in this model. Like basically you can get the real data from like some star. Ideally, you can condition on that. Conditioning meaning like doing Bayesian inference. I think Freddy was also talking about that. Like just before he disappeared, he was saying full-blown Bayesian inference. I'm talking exactly about the same thing. So you condition on your real data, and you get some posteriors over quantities in this model. I can try to explain this better than hand waving, maybe in another occasion, but I would definitely like consider this as one of the things you can do, like to start with.
Is there one of the things that people have tried to do with these models is doing a Markov chain exploration of this to condition to find this, but what people have found is that this becomes very expensive even with this toy model. So yeah,
yes.
the number of, because every time that you add a single spot, so spots are one of the things that break the bank, because every time that you add a single spot to the star, one more spot, you now add 4 parameters to your estimation. And so
sure,
you work with, but with 1 spot, 2 spots, typically people can stay in low numbers of spots. Any more spots will make this prohibitively expensive. Do you have any ideas about how we could speed this up or make it cheaper? Or
yes. I mean, yeah, most of my papers are about answering that question. So there are, so the Markov chain Monte Carlo, the MCMC stuff you mentioned is extremely costly, right? Most of the times, depending on the problem size. There are ways of like making that go a lot faster. Most of these things are called amortized inference. So there are different inference engines. I have one such thing, like in a paper, I can share these things with you. Basically, the idea is to use a bit of deep learning to make Bayesian inference go faster. So you don't do deep learning in like the classical deep learning sense of like you just learn something from your data. There is a way of making use of deep learning for proposing things to sample. Like I think we need to talk about this. We need to introduce the inference pipeline, like a sketch of it or something. But so like you can think about it as like a faster MCMC sampler that has some sort of deep learning magic in it to to make it much more sample efficient. So one of my papers had this example, like I had a particle physics case that is actually analogous to your setting here. Imagine like the latents in particle physics are like the particles' identities, their momenta, like what is going on in a particle detector, right? There is some sort of interaction in the particle detector, but you don't see that. But you have this giant instrument around it at CERN, for example, the Atlas detector or whatever. You have data coming from that. That's like the surface of the sun for you. Like, and the things you are trying to infer is like the stuff happening in the middle of the detector you don't really see. And you have a forward model of exactly of this sort. Like you have a model that models like what sort of interactions can cause what sort of outputs in the detector. Then you do this Bayesian inference. And I think I was supposed to introduce the amortized inference idea. So basically, instead of doing MCMC sampling, you can do something called importance sampling. It's another family of like samplers. And in this importance sampling scheme, you have the notion of a proposal distribution. So this is basically conditioned on data. So how can I explain this? Should I show some slides or something? Or should we do it in a subsequent session? Because this is going into lots of technical details, but like the summary is that like there are ways of increasing the efficiency of this sort of stuff significantly. Yeah.
So if you can tell us just generally perhaps without the slides, and we are going to do something called lining demos tomorrow. So if you want to, you can share with us like a paper that you think
Right.
is particularly relevant to this challenge, and we will. So one of us will take the time today and tomorrow to read it and present it to the rest of us. So
perfect. Okay. Yeah, I have like very good things I can suggest. Yes. So
but tell us generally in words what it means.
In words, okay. You mean this like speeding up stuff, or like what do you which part?
Yeah, the thing that you were considering about showing us slides.
Yeah, so the speeding up, like in high level, like I can say it's like this. So you have this model, right? You sample some parameters, you run it through your model. The model, let's say, simulates the light curve, right? You are simulating light curves in the end. So, and like inference would work like this. So somebody will give you some light curve, single light curve, completely new light curve from some instrument or something. Then you run your simulator millions of times, let's say, with some parameter sampled from a distribution, which we will call prior distribution, right? Then you will compare the simulated light curves with the observed single light curve given to you, and you make a judgment of like which simulated runs are similar to the observation. Then like this is a way of describing inference, like posterior inference. So the distribution of stuff that you sampled and that ended up producing light curves that are similar to your observed light curve, they will define your posterior distribution. So you can do this with MCMC. The speeding up comes from the following. So you run your simulator millions of times, let's say, okay? You keep the data. So every time you run this, you have the sampled input parameters to the simulation, and you have the output, the light curve these things produce. So you have these like pairs of inputs and outputs, right? You keep them around, you put them in a data set. Then from this data set, you can train a deep learning based stuff that learns, given a single light curve, that learns what sort of parameters are likely to produce that. And you make use of this neural network in your Bayesian inference setting. So you don't lose the Bayesian inference pipeline, but you use a deep learning component that you trained with millions of runs of the simulator to make it go faster. And this is called amortized inference because in the beginning, so to train this neural network, you need to run the simulator many times. It is very costly. It takes a lot of effort to train this neural network. But once you do it, you can use it for fast inference later on. Like you have to do it only once. You have to pay that cost upfront. You train that piece, but in practice, after this network is trained, you can do very fast inference with this type of stuff. And the posteriors you get are going to be meaningful under the model. It's still Bayesian inference. Like it's not like a crazy deep learning or Bayesian deep learning stuff where you get distributions, but you don't really know if they correspond to some real posterior. In this thing, you never discard your model. There are ways of like using that neural network piece in a classical Bayesian inference setting. It's a bit boring, high level, low level, technical at the same time, but there's like a lot of things are going on in my explanation. Sorry about that.
Oh, this is awesome. Does anyone have questions for Gunesh?
I have one.
All right.
So you mentioned a lot about the inference scheme, but do you have any kind of idea about the model that we propose? Because the inference, I guess, is just a decision, but the model we propose can sometimes govern the inference scheme. So I'm wondering, like, what did you have in mind when you thought of the proposed model, like hierarchy of parameter, like, you know, just can you speak on that real quick?
So when I was talking about model, I was thinking about the stuff Andres showed, like this light curve generating little piece of program that already seems to exist. I was thinking about either that or some more like accurate version of the same. Like you make it as detailed as you can to cover some, like you need it to be able to produce light curves that kind of look like the light curves people see in practice in real data. If you have that, then you can calibrate that and like do inference. So I was talking about that. Yeah. Yeah. So this sort of stuff is like really, really relevant to what I've been working on. So I will be happy to talk to you on other occasions as well. So just to let you know.
Please, could you be one of our reviewers?
Yeah, why not? Is it like if it's not like the 3 a.m. UK time? Yeah, I can be one of you. Do you know when it's expected to be?
I don't, but I'll see.
Okay, let's see. Yeah.
No, and I think yes, it will be very useful for us to keep you abreast of our progress, and as we start to get your feedback and suggestions, if we can have some of us interact with you more closely in the implementation of something like this. If we decide to do this, is that possible?
Right. Yeah, absolutely. Yeah, it's very, very exciting. Yeah.
Thank you. Any other questions that you would like to ask, or anything that you, Gunesh, would like to discuss that we should consider or be careful of?
Yeah. All right.
Any training gotchas, like, I mean, like in your experience from like anything we should kind of be considered when we make the final decision to choose this method? Like, I don't know, just like a top thing that you learned when you're making it work, I guess. I'm asking.
Yeah, it depends on the thing. I think if you end up doing some probabilistic programming or modeling or inference, you really need to get the basic inference pipeline working before you attempt something more complicated. Like you really need to do the old school MCMC sampler. It's very costly, but you run it for a time. Like you run it for a week or something, you get some baseline out of it that you can trust. That gives you like a baseline posterior in this Bayesian thing. Then you can attempt like more advanced stuff, like I'm talking about the amortized inference, whatever. Like you shouldn't directly go for the most complicated thing, because if something fails, you don't know what fails if you have like a crazy pipeline with 15 things going on. Yeah, I think Andres is a similar approach. Like you should start simple and like build up, like general advice, I guess. Yeah. I'm just beginning to notice Andres's background communicating with the aliens and stuff.
Yeah.
All right.
Yeah.
Anything else? So what is your plan? Like, what are you going to, so this week you are talking about stuff and like collecting information. So it looks like you did lots of brainstorming already.
Yes. Tomorrow we
Nice.
will do like we will look at examples. So from today to tomorrow, everyone is going to go home and look at something that we have discussed or people have used, like for example your paper and the paper of Yaren and things like this. And tomorrow we will actually show how people have tackled this challenge.
Yeah, it was.
Okay, I'm frozen now.
Okay.
What he's going to say is we'll do lightning demos, which are going to be super short presentations, like 2 minutes, where people talk about different things to sort of get a little bit more of a technical input on some of the things and solutions that we've heard about today. And then we're going to start creating solutions out of those.
All right.
For the rest of the summer. Yeah.
Cool. Yeah, I think we have 3 minutes. I had other things like, for example, how do you distinguish like the different contributing factors in the light curves? Like you have like the exoplanets, you have maybe other stuff like magnetic variations. I don't know the term, like, but you have other things that influence that, right? How are you planning to separate like the contributions of each of these things? How do you focus on the spots? I'm very curious.
We have not decided there.
Yeah. So the modeling approach, yeah, sorry to interrupt. The modeling thing can help with that. So if you can model all these things for a given data, conditioning on a given data, the model is going to actually give you some posterior distribution over these factors as well. Like you can get posterior results where you see like some probability of spots, some probability of planets. Like if you can really account for all these things in your modeling, like this can be like a side effect maybe. I don't know much about that, but yeah, it's interesting. Yeah.
Yes, we were thinking about doing everything at the same time.
Okay.
Is that something that what do you think about that?
Absolutely. If you can put all the stuff into one model, like a joint model, like accounting for everything you can account for, like without going crazy, like, I mean, like within the limitations of FTL timeframe, that would be the best thing to do. I would definitely go for something like that.
I'm also typing all this.
Yeah. So I'm going to share the couple of papers, and I don't know. So let's see.
Please, yes, if it's possible before you go to bed, so that the people in the US can look at them while you're sleeping.
All right. Okay.
Thank you so much for your time, Güneş.
Good to see you. See you next time. Bye.
Bye.